So, so
located
what
in
do we
the
have right now? Do you see my screen and do you hear
so
me?
let me just do the introductions. So, good morning, everybody from the Dallas-Fort Worth area in the United States. And today we have three talks, and our first speaker is Mikhail Ignatiev from Saratov State University, and his talk is direct and inverse scattering for differential systems with singularity. Even though we will not be able to see Mikhail's face, but hopefully we will be able to see everything on his talk. Mikhail, please start.
Okay, hello colleagues. So first I should say thanks for organizers to let me participate and let me present my results on such conference to the whole world leading specialists. The talk will be about some scattering problem, and the first preliminary remark that should be made is that scattering here means stationary scattering. In other words, the topic is related to spectral theory of operators, more exactly to spectral theory of ordinary differential operators. And mostly we will be interested in inverse scattering problem, but not only. We also consider some important questions of direct scattering problem. And more preliminary remark, maybe to prevent some questions and maybe some misunderstanding. We will focus only on purely mathematical, purely theoretical aspects. It doesn't matter that the studies, that the objects and problems we consider do not have any relations with applied sciences and engineering. Potentially, they have a lot of applications and a lot of interesting questions concerning numerical aspects. But in current talk, we will discuss only the theoretical and mathematical, purely mathematical aspects. Well, let us go on. Let us take a look at the main object, system one. System one, here y is a vector function with n components, and b, a, and q of x are some matrix coefficients, and n times n, of course. Rho is the spectral parameter. So such a differential system, we will consider it on the same axis, x in 0 to infinity. And at the first glance, maybe we can briefly announce inverse problem. In inverse problem context, we will assume that we know constant matrix B and we know constant matrix A, and we need to recover the function, matrix function Q of X. We will call it as potential. It's more or less usual term. It doesn't mean that it has some particular physical sense. It's just a term with now, it's just word, convenient word. It's more or less conventional now for inverse problem theory. We will use it. At first glance, the system looks like a version of Zakharov-Shabbat system with addition of some singular term x in -1 power. But we will consider the case when n is greater than 2. This case is much more general and much more complicated. And moreover, conditions under which we will study the object are written here explicitly, all are listed here. But some of them are of technical nature. Most important maybe is that BK, which are entries of diagonal matrix B, are non-collinear complex numbers, non-collinear. Several days ago, we have already heard some, no, not some, excellent talk of Professor Vyacheslav Anatolievich Yurko. It was devoted to inverse spectral problems, and he mentioned that it's very important branching. It's branching of principal matter. I mean, we have two significantly different cases. The case when n equals 2 or big case are collinear. This case is, roughly speaking, similar to Sturm-Liouville operator or Zakharov-Shabbat system or Dirac system, something. So main ideas and main methods works the same. And another case is when n is greater than 2 and big case are non-collinear. This case is much more complicated. The differences of principal matter, we can see that the methods working in one case, roughly speaking, do not work in another case. So we consider more complicated in the case, and so we can think that our system looks like a general system mentioned by Professor Yurko in his talk, but without singularity. And also general system of such type earlier studied in now we can see classical works of Richard Bills and Kaufman in 1980s, but also without singularity. So we can consider this. We can consider system one as a system considered by Yurko and Bills plus some additional term with plus singularity, x minus 1 multiplied by some constant matrix A. And let us start with some purely technical remark. It's not most important, but it's most obvious. The term with the singular term, x in minus 1, is not integrable, neither near 0 nor near infinity. This means that we cannot consider the system as a perturbation of the simplest system where in the right-hand side only first term present. We should add also the term with x minus 1. So amplitude system, it's also presented here. It's system 2. It looks like this. It includes the term with x minus 1. It's more or less clear, even if we look only from narrow, pure technical viewpoint. It's already clear that such term will provide at least some technical issues. But of course, this is not the only reason to try to study this system. And let us talk about motivation in more details. So, if we're interested in motivation of studying such type of systems, we should consider the things in more wide context. First, we need to include in our considerations scalar operators, 3. Okay. Pictured here. Both system 2 and the amplitude version of such scalar operator have regular, so-called regular singularity at x equal 0. And such equations and such systems with such type of singularity may appear in many different situations in various areas of mathematics and various areas of applied sciences. And here we mentioned just several examples how we can face the singularity like this. First, and maybe most natural example appears if we consider some partial differential equation or system of equations having rotational symmetry. Then we may separate the variables, and at the end we obtain some spectral problem with what is important to notice that we already get singularity like that. No matter what equation we consider initially. So this type of singularity is not about particular mathematical cases, not about particular physics. It's about geometry. It's about geometry. And it's also important to notice that even most obvious examples are related to the case n equals 2, namely radio-Schrödinger equation and radio-Dirac system. Both are related to the case n equals 2, but we also can consider different situations. Suppose we consider some elastic circular elastic. If you consider circular elastic membrane, we again arrive at the radial version of Schrödinger equation finally. But if we consider elastic plate instead, we will arrive at some differential equation of order 4. But the type of singularity will be the same. Another class of situations where we can encounter the same type of singularity arise from the weighted ordinary differential equations, so the form like this or like this, more general form, and let us maybe it's more convenient to consider the first form with only one term in the right hand side, lambda multiplied by r by y, and we can use some substitution to transform the equation into the form when we will have unity instead of r of x. Something like Liouville transformation and so on. And again, if r is positive, then everything will be okay. But if an equation we have turning point, if r can vanish at some point, then the new transformed operator will have singularity. And in a generic case, the singularity will again be of the same type. It will be regular singularity. And in say in some applications like elasticity theory, like Shell's theory, in Shell's theory you can find equations of order 7, 9, 11 of the form of second form L1 y equal lambda L2 y. And when we have in situation when the turning point appear, we will get equation, we'll get some operators like 3 with regular singularity and of order 7, 9, 11, and so on. And another class of situation where we also can appear, we can face the singularity is if we deal with some integrable PDE, like Cartwright de Vries. It's not that interesting, but we can consider also Cartwright de Vries. But we can consider maybe a Boussinesq equation. And if we try to construct some solutions using various numerous versions of Backlund transform, and we have some transformations with denominators in right-hand side, and if the denominator may vanish in some point, then we again, in generic case, the corresponding so associated differential operator associated via Lax representation with the considered nonlinear equation will also have regular singularity. So what's the point here? We have a lot of motivation, we have solid motivation to consider both scalar equation with scalar operators with regular singularity and systems of equations with regular singularity on the one hand, and on the other hand, we actually don't have any reason to restrict our considerations only with the case n equals 2. Of course, n equals 2 is the most popular case, but it is not the only interesting case. So, a few words about history. I will mention only results, only works related to inverse spectral problems, and we can find a lot of works actually. Study of inverse spectral problems for operators with singularity starts since 1953. It's important to mention this date because we know that 1951 is a year when Gelfand-Levitan paper appeared. So just after 2 years after, specialists remembered about equations with singularity. It's more or less clear why. If we take a look at relation 3, at operator 3, and set n equals 2, then we will see Radzyov-Schadler equation appeared in quantum scattering theory. So it's more or less clear that a lot of specialists, almost all of specialists in the spectral theory, Crane, Faddeev, Marchenko, contributed somehow to the inverse spectral problems theory for such operators and systems as well. And we can see some more families. The list is far from being complete. But there's a specialist who works recently in the area, and they also made some contribution. They made some work, more or less recent works. But all this is true for the case n equals 2. If we are interested in the case n is greater than 2, this study started I think, in 1992, but maybe it is not exactly so. I know the work of Vyacheslav Anatolievich appeared in 1992, but maybe he started before. But the list of contributors is very modest. We can mention only Yurko, Kudishin and Fedoseev, and moreover, Kudishin and Fedoseev were PhD students of Vyacheslav Anatolievich. I should remind again that we actually have no reason to restrict the considerations with only the case n equals. So what do we have here? Really, we can see that including of singularity in the case n greater than 2 was found to be much more difficult, much more complicated thing with respect to the case n equals 2. And that's why there were not that many results related to this case. So what about system one? What about system one? Well, formally speaking, there were no works devoted to system one for the case n greater than 2. But of course, Professor Yakov mentioned deep relation between scalar operators and systems. Moreover, we can say roughly that basic ideas are usually the same. Basic ideas that works for higher order equations, higher order scalar operators and systems are more or less the same. There are a lot of technical difference, but ideas are usually the same. So could your core make some contribution to a theory of system one? Of course, yes. To be honest, it was our initial plan. We had some good grant from Russian Ministry of Science and Education in 2015. And the plan was to extend results previously obtained for the scalar operators 3 to systems 1. But the plan has been changed. The deal is the approach of the method used by your core has some restrictions. It cannot be applied to system 1 without any additional conditions. And the additional conditions are written here explicitly. Most of them is, of course, the last, the condition that the following integral should be finite. So what does it mean? Let me remind that mu with index denotes eigenvalues of matrix A, and they are ordered such that mu1 has the smallest real part and mu(n) has the greatest real part. So actually we have here the function q with indices divided by some power of x, and the power may have any arbitrary big exponent. So it depends on a, and for some a, here you can see something like q divided by x in power 1 million. And we should ask that after such division, q remains integrable near 0. Of course, this condition is very restrictive. It's not natural for applications, and it looks not natural even from purely mathematical point of view. At least we may conclude that if we can study only this particular case, we cannot get a comprehensive picture for the problem we try to study. We may make some aside remark to make the situation more clear. Suppose that we consider classical Sturm-Liouville equation on the whole axis, say, and two types of classes for potential. Potential with Marchenko condition from Marchenko class, and potentials with, say, over exponential decay. We can see that these classes are different. The differences of principle matter. We cannot get comprehensive picture by studying only potential with exponential decays, because properties of spectral objects are specific, special for such narrow class. We have in an example, your solution in case of over exponential decay will be entire function. It is not true for general case, for marginal case. So, no matter how interesting this narrow subclass, we cannot stop at this point. So, actually, and one more observation. Such condition appears only for case when n is greater than 2. For n equals 2, there are no conditions like this. So, and the initial part has been changed, and the new plan was to clarify the situation. And we can announce that we found a way to remove this, not to relax, but to remove this additional condition. And if you take a look to condition 3, we ask of K to belong only to this class of functions L1, and L intersects with LP. And by the way, we don't need to ask to be differential. It was some byproduct, but it's also some result. Okay, let us go further, because maybe spent too much time in this preliminary remarks. So we need to remind some technical details. First, Yoko already mentioned this partition of spectral domain into some sectors, in which in each of the sectors we rearrange somehow decays, and the new ordering is denoted by a capital R with indices, and the ordering is such that real parts of the following products are ordered like this. And F Gothic will be corresponding permutation matrix. So everything is written explicitly. No need to say a few much words. So let's go further, and we should start with the following. Inverse scattering and inverse spectral problems theory is based on concentration of some special solutions. Some special solutions, Professor will mention them, call them Weil solution. In our situation, we will use slightly different because we consider a scattering problem. We will use not Weil, but Weil type solution. Their solution, we construct them for each particular sector as new. And for each particular sector as new, we construct n Weil-type solutions. And kth Weil-type solutions is defined as solution of system 1, satisfying the following additional boundary conditions. Asymptotical conditions, to be more exact, but they play the role of boundary conditions, actually. This asymptotics should be satisfied as x turns to 0, and this asymptotic as x tends to infinity. And we may notice that asymptotical conditions post at infinity are inhomogeneous. We have some inhomogeneity here, namely it is the column, of permutation matrix introduced above. And we may interpret this inhomogeneity as some probing external influence to the system. And then the wild type solution describes system response, reaction of the system to this external influence. So such objects play a key role in inverse problems theory. It's more or less clear. And we found that even on the stage of construction of the wild type solutions, the disadvantages of Professor Core approach appears already. And we need to revisit this stage of the research. Then we will present some details, and let us start with unperturbed case, try to be more or less briefly. In unperturbed case, unperturbed means that Q is 0. Analytical theory of differential equations work. It's convenient to start with the case when spectral parameter is fixed and set equals 1, but x goes x complex and x complex, then we can apply something from some methods from analytical theory. Namely, we can use generalized power series to construct the C case. There's solutions can be considered as some generalization of Bessel solution for case n equals 2 for Bessel equation, Bessel type solutions. And another solutions are normalized at infinity with some exponential asymptotics, and they can be considered as some generalization of Hankel functions. Then we can switch on. Then we can, for the case rho equals 1, we can construct wild type solutions with the following asymptotical properties. Here rho is still 1 and x is still complex. It's not a big deal to construct them. We just need to solve some standard algebraic factorization problem. A condition I is a condition of its solvability. We assume that in what follows, we assume that it's satisfied, and it can be proved that is usually it's satisfied. Well, without details. So after we construct small psi dot, small psi naught, we can switch on the spectral parameter, but set x real and positive are complex, rho complex from some sector as nu, and then construct solutions for amplitude system with arbitrary rho, and in particular psi naught, which is a matrix, where all the wild type solutions for amplitude systems gathered together, n times n matrix. So everything is more or less clear and more or less simple for amplitude case, because it's from the analytical theory viewpoint, it is not a complex case. But we cannot proceed with analytical theory in general case when we have some non-zero Q. And at this stage, we encounter some problem. We could try to, let it be here. We could try to consider general system as perturbation of amplitude system and try to construct some solutions which will be some perturbations of solutions C and E. And this was main idea of your co-approach. And this idea, this approach cannot work in general case because of some reasons. There are no gaps. We have the technical gaps. I mean, in Yoko considerations, uh, in the frame of the approach, we cannot relax the additional condition. Let me recall it. The additional condition like this. So, but finally, we found a way to avoid these difficulties. We we remember uh, some results and some trick of some trick first presented in book of a monograph of Richard Bills, passed date and published to May, classical monograph of 1988. Actually, the object considered in this monograph was absolutely different. They considered scattering theory on the whole line with four higher order differential operator with, say, regular coefficients, formally with coefficients from Schwarz space. Actually, it can be relaxed, but of course, no singularities appeared in their considerations. The case was absolutely different. But some problems they encountered and overcome by their trick, some problems were the same. So let us, that trick is really exciting and beautiful. Let us try to describe the main idea, but not in its original form of Bill's, but for our case, for case with, for system with singularity. So suppose that we already constructed somehow wild-type solutions, all n wild-type solutions. Then what we can notice? If we take arbitrary multi-index of length m, which should be not bigger than 10, of course, and construct such wedge product, that we find that this wedge product will be also solution for some system of ODEs, some auxiliary system. Of course, it will not the same system as initial system, some different system. But what is important here, this observation, actually here wild-type solutions are written, but we can replace them with any other set of solutions of the system, of system one, any set of M solutions with the same row, and then the assertion will remain true. So such wedge product will also satisfy the same auxiliary system. Auxiliary system depends only on M, only on length of multi-index, only on how many solutions of initial system will take. So this observation is not specific for wild-type solution, but next two observations are specific. Suppose we consider the following set of tensors. First tensor is just first a wild-type solution, which have minimal growth. Next is psi1 wedge psi2, then psi1 wedge psi2 wedge psi3, and so on. Each of such wedge products have a minimal growth as x turns to zero, to infinity. Minimal with respect to what? With respect to other solutions of the same auxiliary system. So this is main idea, and what to do with it. The idea is let us not to try to construct well-type solutions explicitly, but first construct the tensors from some well-type equation, and then decompose the tensors to find well-type solutions themselves. So now some technical details. Unfortunately, we don't have that much time, so we skip most of technical details just to illustrate main ideas. Well, we consider the Walter equation like this. Walter equation like this. When both kernels and free terms are constructed in terms of amplitude system, somehow. And we can prove that both equations are unequally solvable, and we call their solutions as fundamental tensors. From the equation, from the Walter equation, we can find some properties of fundamental tensors. They are collected in theorem 1. Well, we can see that fundamental tensors for general system is perturbation of corresponding fundamental tensors for amplitude system of some, roughly speaking, small addition, small up to the sum, up to some weight function. So after we obtain some properties of fundamental tensors, we decompose them and find and construct in such a way. Thus, we construct well-type solutions. How it works? How it works? For each particular rho and for each fixed x, we should consider the following linear system. Here, f with indices and t are already constructed above fundamental tensors, and psi is a known vector. We can prove that such overdetermined linear system is uniquely solvable if corresponding characteristic function, which is defined like that in terms of tensors, is not doesn't vanish. And after all, finally, we found that we can find everything we want about the wild-type solutions, only from this system. The following theorem presents some results. So if we construct the construction like this, roughly speaking, divide metrics of wild-type solutions for general system, divided, roughly speaking, by analogous metrics for amplitude, then we can control behavior of such construction. If we consider only, if we take some set in spectral in raw plane and consider only the class jp dot of L of the functions for which no roots of characteristic functions appear on this particular set, then if we are interested only in potentials from this particular class, then the result can be written in more convenient way. So general wild-type solution is perturbation of wild-type solution for amplitude system with some, in some sense, small additional term. So let us go to the inverse problem. Inverse problem. Let me announce that we restrict our consideration only with the situation when characteristic functions, all characteristic functions have no zeros at all. It's a very special case, but it is non-trivial. Roughly speaking, this is the case when the discrete spectrum is empty. So we decided to start with clarifying the situation with continuous spectrum. We should take a look again to the initial picture with partition of spectral domain on subsectors. And now we are interested in the rays which divide sectors between each other. And we can introduce limit values for matrix consisting of wild-type solutions, psi plus and psi minus. If we take rho on sigma nu, then psi minus contains limiting values of wild-type solutions. When we go to sigma from S nu, and psi plus analogous if we limit values if we go from S nu plus 1. Let me be a little bit more brief that I planned. Yes, we have no much time. So of course, we have some conjugation between these two limit values because both psi plus and psi minus, both their matrices satisfy the same system, namely system 1. That's why they should be related via such type conjugation condition. And we use V, matrix V, as a scattering data. In general case, if discrete spectrum appears, we should also add some information about discrete spectrum. But anyway, matrix V will also be a part of scattering data. But we consider only relatively simple special case. And we should start with investigation of properties of scattering data. There are some properties, of course, but we don't have sufficient time to put much attention to them all. But we should mention at least one of them, namely Theorem 6. Theorem 6 is formulated for more general case. In this case, in the Theorem 6, discrete spectrum is allowed. It's possible, it's maybe not empty. But we ask that characteristic function, all characteristic functions do not vanish at 0. Not vanish at 0. So, namely, speaking more exactly, such limit for each particular sector is nu, such limit do not equal 0. If this is the case, then matrix V has limit values as rho tends to 0 from it's misprint, it's not S, should be sigma should be written here actually. So if we go to 0 from each particular ray, then we always have some limit value, some finite limit, well-defined finite limit for matrix V. This limit value will depend on sigma. For different rays, it can be different, but it does not depend on potential, on Q. So it's the same for all potentials. This property is very interesting because if we consider system 1 without singularity, then we encounter no analogous properties appear. This is most characteristic property of scattering data for systems appears due to presence of singularity. And it was important to find this property, and it was important to use a tensor technique. It plays also key role. So we may skip some details. And here the formulation of inverse problem, given function V, matrix function V, posed on union of all rays, recover potential Q. And we can reduce this inverse problem to some linear equation, main equation. It's written here. Both operator A bold and V hat can be constructed from scattering data and amplitude system. Actually, they are all written explicitly. You can see how it works. And the operator looks like that, and it constructed in terms of singular Cauchy type integrals like that. So, and one of important result is that operator A is invertible for each x. So solving this linear equation is well-posed problem. It's not about inverse problem at all. It's just about linear equation. But it's also important result for applications. So then after we solve the main equation and find the following value, P with hat, then we can take this P with hat and recover the desired potential via some explicit formulas. In the simplest case, when Q is identically zero near zero and near infinity, it's most simple. It looks like that. Square brackets denotes matrix commutator. In general case, we have more complicated situation. We needed to introduce some linear operator as a strong limit of some operators, and some bilinear operator which acts on the pair of V hat and P hat. So it's actually some passing to the limit procedure. It's technical, but finally everything works good. We still have some explicit formula for recovering the potential. And I can see I have only 3 minutes. And I can just provide brief announcement to the following result: characterization of scattering data. The problem formulation looks as follows: given some matrix V, arbitrary matrix V, posed on the sigma, and we want to understand whether there exists some system of the form 1 with Q from the corresponding for specified class, for which this given arbitrary matrix will be scattering data. And the answer is here. The answer is here. Actually, it looks like the analogous results of presented in Tokov-Yelko. It takes some a priori conditions. We ask that V should be taken from some class V bold. We ask that some operator is invertible, and we ask the result potential is belongs to the class 6p, but we don't ask that the resulted potential have no discrete spectrum. We can, the condition 2 actually is to check that a priori check. Before we recover the potential, we can check that discrete spectrum for resulted potential will be really empty. This is important in my opinion, because otherwise we ask customer to go back to spectral domain after he recovered the potential. He started from spectral domain, goes to spatial domain, and then go back. It's not good from my opinion. And the last slide, important, in my opinion, important thing, we can provide some sufficient conditions for solvability. Roughly speaking, if we take matrix which is sufficiently, which has sufficiently good analytical properties, and which is relatively small in a uniform norm perturbation of V dot, then it's we can be sure that it is a scattering data for some Q having from the specified class and having empty discrete spectrum. In my opinion, sufficient conditions of such a type are important because they shows that our a posteriori conditions like 3 and first do not hide some misunderstanding. We did not lose some important property when we investigated properties of scattering data. We didn't lose no important property which now hidden by a posteriori conditions. So that's why I think that results of such type are important, and they are not usual. Actually, it's not that easy to find even such rough, but some sufficient conditions for higher order case. So I think that's it because the time is over. Well, thank you. If any questions, please.
Well, are there any questions?
Yes, I would like to ask, so you mentioned some properties of the solution. The solution that you find is unitary?
What exactly you mean? What type of solution?
The solution, so you solve a differential equation for y. Now, this is essentially the Schrödinger equation. Just you choose
no,
some...
No, it's not Schrödinger.
No? Why?
No,
it's a first order differential equation. It's just recasted in some different parameterization. But this is a Schrödinger type. It's a singular Schrödinger type. equation.
Only if n equals 2. If n is greater than 2, it's not Schrödinger equation. It's moreover, it doesn't look like a Schrödinger equation. It's
Right,
very
it's the
far
first
from
order.
Schrödinger equation. We
Yes, if I
consider
may-
the case of n greater than 2. It's not look like Schrödinger equation.
Yes, remember, this is a system, an n by n system. It's an equivalent to one single differential equation of order n. And the Schrödinger
Yes.
equation would happen when n equals 2.
I'm not sure why is it restricted for n equal to, but even in this particular case, the solution that you find in this way is unitary, or is it violating unitarity? I just wonder.
You mean the case n equals 2? No, I don't know, actually.
So would you please
Actually.
explain what you mean by unitary, a unitary solution?
Well, unitary is a probability preserving solution, meaning that the exponential solution that he showed is actually preserving unitarity, because this type of evolution, if you apply u and you take its conjugation, then you get the same thing independent of the value of x. So there is a clear condition of what is a unitary. So unitary meaning that the solution that he finds, if he applies the conjugation or like the self-adjoint and multiply by u, then it will remain equal 1.
No,
Yeah,
no, nothing like that. Nothing like that. The situation is much more general and much more complicated. The question makes sense only if n equals 2, and even in this case, I'm not sure. But you see, in matrix B, we have complex values which are not collinear, which are distributed somehow in whole complex plane. Nothing like unitarity or self-adjointness. It's far
if you
from this.
replace the whole thing which is inside the brackets, everything, the row B and the inverse of XA plus the Q, then you call the whole bunch of terms just H, your Hamiltonian, which could be non-Hermitian, for example. Then this is a first order Schrödinger equation, but okay, even if you don't see it. I just wanted to mention that I actually dealt with relaxing this condition that you mentioned. And indeed, this is kind of unnatural condition because it's a singular problem. Then therefore you would expect that some interesting physics will come up if you relax this condition and you get rid of it. And I dealt with this case, and the L2 will not be a good assumption. It's inadequate space for dealing with the real complexity of singular problems, as you actually mentioned, because of the inverse of x in your problem. So, just as a general comment, I would say. It makes sense to...
You see, this conditions is very natural for this mathematical problem. I don't agree with this remark. It's the most natural conditions. It's not possible to suggest more natural.
No, it's a natural condition if the space is L2, but if you study some more difficult spaces like Crane space or some other spaces, then it makes sense also to see what can happen if you remove it.
But if you like to study other spaces, no problem. But for this investigation, the author chooses the most natural situation.
Yeah. I mean, it makes sense to study also on these spaces, but other spaces will put you in some difficulty to proceed with this approach, I think. Because the condition is just unnatural for some spaces. For the spaces that you choose, it's okay.
Well, are there any other questions? In fact, may I ask maybe one or two short questions? Now, when you have the scattering matrix defined as the matrix relating the psi plus and psi minus, well, in case there are so-called bound states, how do you deal with the bound states? Are the bound states going to be obtained from the scattering matrix? Are they going to be, for example, as related to this? I guess do you separate
actually,
the scattering matrix as some reflection coefficients and transmission coefficients so that the bound states can be obtained, say, from the poles of the transmission coefficients, for example? Or you don't deal with the bound states at all. You don't deal with any square summable, square integrable solutions.
I guess I'm more or less clear with your question. Well, currently, at the moment, I have complete results only with additional condition that discrete spectrum is empty.
Oh, that's right.
But I need to make some remarks about motivation, maybe. So I assume discrete spectrum is empty, so no bound states. But I don't see any problem for situation when we have discrete spectrum separated from continuous spectrum. If we have no discrete eigenvalues, which are lies were located on sigmas. There, I don't see any problem. But I do want to start with this case because of the following. I mentioned some property. They shows that most interesting things specific for presence of singularity are located in spectral domain near zero. And if we consider only eigenvalues, discrete eigenvalues separated from zero, it will be non-specific. It provides some technical issues, but it provides not new information about a singular case. Most interesting case for the system with singularity, and the case from which we should start, in my opinion, is the case when zero, rho equals zero, belongs to discrete spectrum. That's why I decided to not to get some particular results, but start with the most difficult case. Until that, the question you asked is absolutely unclear. Formally, currently, we don't know what to do with. We don't have a results. We have some ideas, but we don't have results about the situation with discrete spectrum. If I understand you correctly, bound states, we also call them discrete eigenvalues. Yes, they are roots of characteristic functions. So we have no results. We have ideas, have no results, but we start from most difficult case, because all the other cases are actually not interesting at all.
Okay, well, thank you. Are there any other questions? Well, if there are no other questions, we thank our speaker, and so we will resume in 6 minutes. Thank you.